Can you help me to go?
So let's begin. The first talk on the panel, the talks will be 12 minutes, and I'll set the timer to indicate the time after 10 minutes. That will give you 2 minutes to finish up. The first talk will be given by Dr. Mueller from IBM Zurich. Title of the talk is A Road to High TC Superconductivity, Experiments with Alkaline Earth Substituted Lanthanum Copper Oxide. Dr. Mueller.
Well, I think according to the schedule, my talk is now over. Yeah, I have entitled it A Road Towards High Temperature Superconductivity, which George Bednarz and myself think we have found. There may be other roads to achieve that. Now, what has been achieved? I have plotted here transition temperature versus the years where they have been achieved starting from the discovery in 1911. And you can see from that graph that if you would extrapolate more or less linearly as a function of time, you would expect that by 1919 you would have reached about 30 degree Kelvin. Instead of that, already by the end of last year, one had exceeded this extrapolation by quite a bit. And by now, here I have plotted the confirmed results by the group of Professor Chu is well toward the 100 degree Kelvin. Now, the first observation in the new system dates back in January 27, when we saw the onset in the lanthanum barium copper oxide mixture. And by optimizing the substitution of the lanthanum by the barium, we were in April up in the 35 degree Kelvin range. And I show you the data which we submitted at that time. So essentially, the whole search extended over about 2.5 years. It was strictly a two-man project. Not even a technician was involved. It was George Bednarz and myself. And you see here that the resistivity as a function of temperature decreases metal-like, and then has a tendency to localize, and certainly you get the onset. And for example, for this sample, we couldn't measure, at least with our equipment anymore, any resistivity. Now, how did we find this material? Well, we had a concept for high TC superconductivity. Namely, I had come to the conclusion that one should radically abandon intermetallic compounds. There had been many groups who had tried to improve the TC in this area, but do a search in metallic oxides. What was the rationale of doing that? Well, in '73 at San Diego, they found a TC of 13.7 degree Kelvin in the lithium titanium spinel, and 2 years later at DuPont, Slide and co-worker found in the barium lead bismuth oxide a comparable high TC. Now, working in this area, both the group of Dr. Batlock here and the group of Dr. Tanaka found that the carrier concentration was of the order of 2 to 4 times 10 to the 21, which is about an order of magnitude less than what you have in a normal metal. And this was remarkable because this carrier concentration multiplied by the electron-photon interaction is essential for in a normal BCS superconductor, the formula stands here. So that means that this electron-phonon interaction had to be very large, and one could expect if one would try some other oxide, one may do better than that. So this was part of the concept. The other part of the concept was to restrict our search strictly to metallic oxides containing nickel and copper only in octahedral coordination. Why? Because they have partially occupied d orbitals which point toward the oxygen ligands. And therefore, this was our view. One would have a large interaction between the metal and the ligand. You see here the octahedron and a copper inside. And if you have a 3-valent copper, you have these z-square orbital occupied ones and these x² minus y² orbital also occupied ones. And they are degenerate in energy. If you have a 2-valent copper, then the further electron goes in this orbital here, and you get an elongated octahedron. This is an expression of the Jahn-Teller effect. Now, I would just say here, it may be important in theory to consider, especially also in the new compounds, the degeneracy between these two orbitals, and not make a theory only for a single band from x² minus y orbitals. For instance, Don Lee, in a very recent theory, has done that, and he will talk about that later on in this session. Now, another thing is that what is the interaction? How does the oxygen move? Well, you have basically two modes, a Bressing mode and a Jahn-Teller mode. The Bressing mode is shown as here. It changes the volume. And the Bressing mode is very attractive if you have, say, bismuth or lead, like in the bismuth-lead perovskite, because the bismuth and the lead tend to disproportionate. So this is a disproportionating mode in a way. On the other hand, here is the Jahn-Teller mode. You cannot distinguish in the xy plane the motion of the oxygens between the Jahn-Teller and the Bressing mode. It's only the out-of-plane motion of the oxygens which is different. Namely here, the red arrows show 180 degrees out of phase. And it's not a matter of so much of the amplitude, but of the phase. And to my understanding, there has not been experiments till now to distinguish between these two modes. This mode here preserves the volume of your octahedron, and this may be important because the copper ions, in general, as far as I know, do not disproportionate. Now, the structure which we found is this potassium nickel fluoride 4. It's a layer structure, but this structure is tetragonal, whereas the one we have is slightly orthorhombic. What you have is sheets of copper oxygen 6 octahedra, and in between you have layers of lanthanum oxide. And these octahedra, they are now not in a plane, but they are slightly tilted along 1,1,0 directions. If you don't substitute the lanthanum by, say, barium or strontium, by an alkaline metal ion. So without substitution, it's orthorhombic. And when you substitute, it gets tetragonal, as exemplified here by this X-ray data as a function of the barium content. So it's split here, and smoothly you see only one line. Here it's tetragonal, and it's around here at this concentration where you have the optimum transition temperature observed in these layer compounds. And I showed you our data for the orthorhombic case, case in between number 2 and 3 for optimum transition temperature in these layer compounds. So without, or barely without barium, you have the following thing. The resistivity as a function of temperature first decreases linearly, and then it strongly localizes. And the resistivity alone may be typical of something which is, has the behavior of a semiconductor, but the susceptibility, which is plotted here, is almost temperature independent, Pauli-like. So the statistics is still the Fermi-Dirac statistics, despite that the motions become slower. This has been termed a Fermi glass behavior by Anderson. 2 minutes only. Oh. Now, in sample number 2, the onset here is somewhere around 27, and sample number 3, the resistivity onset is higher up, and the diamagnetism was it was becoming diamagnetic here at a lower temperature than here, so it was a systematic increase in Tc, and we thought we have really, because it's becoming diamagnetic, superconductivity. Now, when we were asking ourselves, we had submitted this paper. One Monday morning, Dr. Takashige, who is from Japan, came to our laboratory and was quite excited because his wife has read over the Sunday the international edition of the Asahi Shinbun journal, and he found this, which essentially was saying that in Tokyo they had confirmed our results. We were very pleased with that. So now I'm going to just flash at you 3 view graphs before quitting. One thing is that in these compounds, in part, you have flux trapping and some superconductive glass state where you have, if you field cool it, it's reversible. If you zero field cool it, you have irreversible states. This is indicative of a superconductive state. Those who are interested may find further information in this week's physical review letter. Another thing what I wanted to say is the structure of the new compound, which has been determined in IBM Yorktown and IBM Almaden. You have essentially now a perovskite, a lattice, where you have barium, yttrium, barium, and this also shows up in transmission electron micrographs. In some of the layers, which I have not time to say, you have oxygen vacancies. And if you are interested in applications, then you may look at this result, which is, has been done at IBM Yorktown Heights over last weekend. It shows you the resistivity now over of a 400 nanometer thick film, which becomes superconducting here at this temperature, and because it's a film, is proof that some technical applications are possible. And with this, I thank you for your attention.
Thank you very much.